Today we have to discuss about Arrhenius theory of electrolytic dissociation. Arrhenius theory of electrolytic dissociation. This theory simply we can say it as ionic theory introduced by Arrhenius. It has many merits and additionally we have some observations supporting the postulates of Arrhenius theory, and finally we will go to the limitation of this theory. At first we have to see the main points or postulate proposed by Arrhenius in this theory. He actually proposed all these theories or all these postulates after conducting many electrolytic experiments. He mainly observed that electrolytic solutions conduct electricity and they can exhibit abnormally high colligative property. Actually, the colligative property you have studied in the chapter solutions. Anyway, we have to go through the postulates one by one. According to Arrhenius, electrolytes, when dissolved in water, they can dissociate into electrically charged particles called ions. For example, when an ionic compound NaCl is dissolved in water, it can dissociate into Na++ Cl-. That is the proposal of Arrhenius in this theory as his first point. Second one, the dissociation of compound occurs in such a manner that total charge on the positive ions is equal to the total charge on the negative ions. Then only the total charge of the electrolytic solution remains zero or solution become neutral. That's also correct in the case of NaCl. If we are taking 1 mole of NaCl as electrolyte, when it is dissolved in water, we will get 6.02 into 10 raised to 23 Na plus ions and 6.02 into 10 raised to 23 Cl minus ions. Total charge of negative ions and total charge on cations or Na plus ions are equal. Then NaCl solution remains neutral. Third one, at finite concentration. That means any concentration before reaching infinite concentration. At finite concentration, electrolyte will be only partially ionized to a degree dependable on many factors which include nature of substance, concentration and temperature. Fourth one, the ions formed from this partial dissociation are in state of dynamic equilibrium with unionized molecules. That means when acetic acid, an electrolyte, is dissociated in water, we will get CH3COO minus plus H3O plus or H plus. If 56 molecules or 56% of some molecules are dissociated, we will get 44 undissociated molecules and 56 dissociated ions. These 56 and these 44 are not always constant. There is an equilibrium between dissociated and undissociated. When two ions from right side combine to form acetic acid, then one acetic acid dissociate into two ions. When 4 ions combine to acid, then equally acid dissociate in this direction. So there is an equilibrium can be established between the dissociated and undissociated. So for Arrhenius, even strong electrolyte also undergo partial dissociation at normal condition. When we are diluting, dissociation increases. That is his proposal. That is actually a wrong proposal. His statement is correct in the case of weak electrolyte, but it is not in good agreement with strong electrolyte. Fifth one, the extent of ionization varies with concentration, becoming greater with increased dilution and reaching maximum at very high dilution. Extent of ionization varies with concentration when concentration decreases, or in other words, when dilution increases, more and more molecules undergo dissociation and reaches at maximum value at high dilutions. The ions are free to move independently under the influence of applied electric field. Positive ions move towards the negative electrode and negative ion move towards the positive electrode. These all things we have seen in our first class during the electrolysis of NaCl solution. We have seen that the ions of H plus move towards the cathode having negative charge. That means H plus is positively charged and move towards oppositely charged or negatively charged cathode and discharged there as hydrogen or liberated as hydrogen. And in the same way, negatively charged Cl minus ions or chloride ions move towards the anode having positive charge, and there they undergo oxidation and liberated as chlorine. That is the main content of the 6th point. Seventh one, the conductance of electrolyte solution is due to the migration of ions towards the oppositely charged electrode. Greater the ionization, greater is the conductance. That is also good. When electrolyte is dissolved in water, they dissociate to oppositely charged ions and they will migrate towards the oppositely charged electrode. And this migration or movement of ions are responsible for the conduction. If electrolyte undergo greater ionization, greater will be the number of the ions and greater will be the conductance. With respect to the colligative properties, ion act in the same manner as an unionized molecules. This you can study very clearly in solution, especially I think in the part of osmotic pressure and colligative properties. When we are adding 1 mole of urea to water, that is not an electrolyte, that is a non-electrolyte. That means when urea is added to water, there is no chance of dissociation or ionization. So that urea in water produce 6.023 into 10 raised to 23 particles, number of particles. Actually, colligative property is dependable on the number of particles and not the nature of particle. At the same time, when 1 mole of NaCl is added, their number of particle is not 6.02 into 10 raised to 23. There we have 6.02 into 10 raised to 23 Na plus and 6.023 into 10 raised to 23 Cl minus. Then in effect we can experience double number due to the dissociation of electrolyte. So the colligative property in electrolytic solutions are much greater than our normal expectation. Ninth one, the properties of electrolyte in solution are properties of ions they furnish. The properties of acids and bases are respectively due to the H plus and OH minus ions they furnish in solution. In a solution of electrolyte, we can expect the properties of corresponding ions only. No other expectation can be permitted from that solution. Example, in an AgNO3 solution, we can expect the reaction of Ag plus or the reaction of NO3 minus. In that solution, we have no scope to expect the reaction of Cl minus or barium 2 plus. With these 9 points, we have concluded Arrhenius' theory of electrolytic dissociation. Now we have to see some evidences supporting the proposals or suggestions of Arrhenius theory. First one, electrolysis. According to Arrhenius, when electrolyte is added in water, electrolytes split into positively and negatively charged ions. They move in solution and move towards the oppositely charged electrode when we are applying potential difference in the solution using suitable electrodes, and the positively charged ion move towards negatively charged electrode and accept electron from there and undergo reduction and deposit or discharge or liberate. In the same way, negatively charged ions move towards the positively charged electrode, that means anode, and there they can liberate their electrons and they get oxidized and deposited or liberated. When a potential difference is applied across two metal electrodes dipping in the solution of electrolyte, the ions move towards the oppositely charged electrodes and give up their charges. Negative ion is neutralized by losing electrons at the anode and positive ion by gaining electrons at the cathode. Thus, after losing their charges, the species are deposited or liberated as atoms or molecules. This explains the chemical decomposition, that means electrolysis caused by the passage of electricity through an electrolytic solution. But solutions of non-electrolytes do not produce ions and thus are unable to conduct electricity. These are observations which actually support the suggestions of Arrhenius theory. In the same way, another evidence is increase in molar conductivity with dilution. When an electrolytic solution is taken and on the addition of water continuously to the solution, that means we are diluting the solution, degree of dissociation increases gradually and the distance between the ions increases and slowly the conductance of the solution increases. This observation also support Arrhenius theory to greater extent. Then third one, ionic reactions. When an electrolyte is added to water, that electrolyte undergo dissociation to positively and negatively charged ions, and that ions participate instantaneous reaction with other ions which are coming in contact with the solution. Example, when we are adding AgNO3 to NaCl solution, at first we have to take NaCl in a test tube, NaCl in water, that means NaCl solution. This solution does not contain NaCl, instead they contain Na plus and Cl minus separately. To this we are adding AgNO3 solution which contain Ag plus and NO3 minus. Instantaneously or at the moment when AgNO3 come in contact with NaCl solution, definitely there will be the formation of AgCl as precipitate. AgCl precipitation takes place. This also supports the statement that when dissolved in water, electrolyte become independent ions. That was one of the first proposal of Arrhenius that is supported by these observations. Fourth one, abnormally higher colligative properties for electrolytes in aqueous solutions as compared to those for non-electrolyte. This concept I have already been explained using urea and NaCl. Osmotic pressure, lowering of vapor pressure, etc. are the important colligative properties that you have studied, and these properties are anomalously higher for electrolytes in water because of their ionization. Due to their ionization, number of particles in solutions are much higher than the normal expectation. Each ion behaves as an independent particle and contribute towards the colligative property of the substance. These are the four evidences supporting Arrhenius theory. Even if this much of evidences, this much of proofs we have to support Arrhenius theory, there are many limitations also. That also you have to consider. First one, here we have to consider limitations. Arrhenius theory simply assumes the presence of ions in aqueous solution of electrolyte. It does not explain why such ionization occurs in water. Arrhenius theory proposes the ionization of an electrolyte in aqueous solution, but actually all electrolytes or ionic compounds cannot be ionized in water. Ionization is possible only if the hydration energy released will be greater than the lattice energy of that compound. Such any explanation could not be forwarded by Arrhenius. He simply says that any electrolyte in aqueous solution dissociate or ionize. That is not true. He could not explain the reason behind such ionization. Second one, anomalies arises when Arrhenius theory is applied to strong electrolyte. Example, Ostwald dilution law, which we have to see later in this chapter itself, and also you can see in Ostwald dilution law in ionic equilibrium, which actually true in the case of weak electrolyte. That is completely wrong in strong electrolytes. It completely failed in strong electrolytes. Actual reason for this failure is that Arrhenius proposed a concept that when electrolyte is dissolved in water, they are partially ionized. When it is diluted with water or on the addition of water again and again, they undergo more and more dissociation, then number of ions increases. This is true only in the case of weak electrolyte. Actually, strong electrolytes are completely ionized even at moderate concentration. So, Arrhenius concept is not in good agreement with strong electrolytes. Third limitation is Arrhenius theory takes into consideration the ionization of electrolyte that takes place in presence of water. Does not consider the ionization that occurs when electrolytes are in fused state. According to Arrhenius, an electrolytic solution can be prepared only when that electrolyte is dissolved in water. We have many other solvents, and also we have fused solution also. We have studied about the electrolysis of molten NaCl. On electrolysis we will get Na plus and Cl minus ions, and Na plus move towards the cathode to deposit as sodium, and Cl minus liberated as Cl2 at the anode. That also we have seen in the previous classes. That condition could not be explained by the Arrhenius. He explained only in aqueous solution. Arrhenius theory, fourth limitation, Arrhenius theory assumes independent existence of ions but fail to account for the factors which influence the mobility of ions, such as electrostatic force of attraction between the ions. According to Arrhenius, when an electrolyte is dissociated in a particular solvent, especially water, then that ion is completely free to move throughout the solution without the influence of any counter ion at any concentration. Actually, that statement is wrong. Before reaching infinite dilution, all the ions are moving under the influence of oppositely charged ions. Means, in an NaNO3 solution, Na plus ions move under the attraction of NO3 minus and vice versa. In NaCl, Cl minus ion is moving under the influence of Na plus, and it is true in the case of Na plus also, which is moving under the influence of Cl minus. So, at any concentration, this kind of free movement is impossible in electrolyte. That is possible only at infinite dilution, where interionic attraction vanishes. But actually, in Arrhenius theory, he could not propose such explanation on the intrionic attraction or electrostatic attraction between ions. Fifth one, degree of dissociation alpha of strong acids and bases, that means strong electrolytes, were found to decrease with increase in concentration. In view of this fact, Arrhenius theory could not explain why the heat of neutralization of strong acid with strong base is found to be independent of concentration. In thermodynamics, you have studied this fact that heat of neutralization of strong acid against strong base is always a constant, that is around 46 kilocalories per mole, I think. But according to Arrhenius theory, that observed fact cannot be explained. Sixth one, the theory could not explain the variation of transport number of ions with concentration. Transport number is the current carried by a particular ion out of the total current passing through the solution. That we can see in the last part of this chapter. That transport number could not be effectively explained by the Arrhenius theory, especially the variation of transport number with concentration. These are the major postulates, evidences and limitations of Arrhenius theory. Even today, in spite of all these limitations, we are accepting Arrhenius theory in explaining the electrolytic phenomena to greater extent and depend on the Arrhenius theory. Thank you.